everyone. So I have two sessions today. In both the sessions, we will discuss high performance X computing. If you search in Google, you will not find this word. X computing. High performance X computing. You will not find this phrase in Google. Why I have given this title? Because there are so many computing paradigms are there. Like in the first talk, Professor told about parallel distributed computing. We have cluster computing, we have grid computing, now we have cloud computing. So these all are called as high performance computing. And there is a book written by one of the top most authors in computer science field by Professor Asst. He has mentioned the book name is High Performance Cluster Computing. So basically, that book is having two volumes. In the first volume, you will get more or less theory. Second volume, you will get programming paradigms, like how to write NP programming in cluster, how to use OpenMP in the cluster. That's why I've given this title as High Performance X Computing. So we have to integrate HPC with any other computing paradigms. It may be cluster, it may be grid, it may be cloud, it may be any other type of computing. That's why the title is like this. Okay, these are the content you can expect in these two sessions. We'll start with some motivational example. Why computing is important. Like Professor Asst also mentioned about two important things. One is computing, another is called as communication. So for every type of application, first we need to decide whether computing is dominating communication or communication is dominating computing. After that, you have to decide whether to go for HPC or not. In some cases, we have seen communication is more important than computing. Vice versa is also true. So one of the informal example we can say, suppose I have 2 minutes of work at Hyderabad. I have 2 minutes of work at Hyderabad, but I have to travel from Warangal to Hyderabad. It took, let's say, 3 hours. Okay. Let's say that work is called as computation. So I have a computation of 2 minutes only, but communication is 3 hours. You have to go and 3 hours you have to come. Totally 6 hours. So in this example, what we can say, communication is dominating computation. Okay. Other cases you can say transmission, let's say, takes 2 minutes time, but you need computation of more than 1 hour. So in that case, computing is more important than communication. Irrespective of this topic, we assume that computing is important than communication. When you say communication is important, there is no word called HPC. HPC primarily focus on the computation, not communication. There is a communication, but the time is very, very minimal. Okay, so some of the examples we will see. Then I'll tell you about the trends of computing, starting from parallel distributed computing till cloud computing. I'll tell you. Okay, so this is one of the roadmap. I'm very much interested in this roadmap because you should know as a computer science student or faculty, starting from the first computer till date, what are the technologies there? It is not a complete list, other technologies are there. Whatever I have identified, I have represented in the form of this roadmap. So you know, father of computer is Charles Babbage. So that is not a full-fledged computer system, but he developed the concept. That's why he called that is the father of computer. So it is long back. That is 1822. So almost 200 years back. So he formalized a computing machine, but that is not a full-fledged computer system. Then in 1930, we have mainframe computer. In every country, getting mainframe computer is again difficult at that time. Hardly one country is having only one computer, mainframe computer. Because the size of mainframe computer is very, very huge. And there are so much electronic components are used in the mainframe computer. So it is difficult to do processing, and it is difficult to go to the mainframe computer and process that. Mostly people use the remote access. Then in 1945, ENIAC is started. It is called as Electronic Numeric Integrator and Computer. ENIAC. It is, although it is what is that electronic, but it is not said to be the fast electronic computer, because the word electronics is there, but still it is not called as fast electronic computer. But after that, after ENIAC, people have developed an improved version of ENIAC that is called as EDVAC. That is electronic discrete variable automatic. Okay. So EDVAC is generally said as a fast electronic computer. In what? Right? What is the difference between these two? ENIAC and EDVAC? That is important. Now you know, everybody knows that we use binary number system, right? In our computer, everything is stored in the form of 0 and 1. But ENIAC case, it is not true. ENIAC stored everything in the form of decimal format, not in binary format. So the fast computer which is started, that is EDVAC. That is the reason why it is called a fast electronic computer. Okay. Size is very huge. Obviously, cost is also very huge. Okay, there are so many vacuum tubes are there. So many transistors are there, resistors are there, capacitors are there. The size of the computer is very, very huge. But till 1950, there is no concept of parallel computing. Nobody has thought that we can do multiple work simultaneously. Okay. Then people thought that why don't we do multiple works at the same time? Whether it is a scientific application or it is an engineering application, before 1950, everybody used only nine-thread computer. Okay, or sequential computer. Computer is not capable to do parallel. Okay, 1960 people have started with large-scale computer system architecture. So they thought that like there is two kind of developments we can do in our computer system. Like suppose I have 4 GB of RAM, I want to enhance my capacity, so I am putting another 4 as a parallel slot, which makes it is 8 GB. Right? That is one type of development. We are enhancing the speed of a computer system. Another thing, what you can do, you can combine multiple computers. Let's say 2 computers with 4 GB each, and we got 8. These 2 ways. I am enhancing the capacity of a single computer system. Second case, I am not enhancing a single computer system, I am combining with other computer system. Together I can achieve. Like in a computer lab, we have 30 and 40 computer system. If each computer system is having 4 GB, so together we have 4 into number of systems. That much GB of RAM. Or if 1 GB hard disk, 1 GB into number of systems, that much storage we have. Then in 1967, people started with cluster computing. The name says cluster. The dictionary meaning is called as group. Okay. So group means the similarity is more. If 2 people belongs to 2 different groups, there is some dissimilarity. Like that's why they belong to 2 different groups. So what cluster computing suggested? You can combine multiple computers. One computer is act like a cluster manager that will handle rest of the system. Just like master-slave architecture. Right? One is treated as master. All other computers are treated as slaves. Master will assign some work to the slave. The slave will do that work and return the result to master. Again, master is consolidating the result, return to the cluster. So that is the use of cluster computing. But more or less, cluster computing is similarly, we have a concept called local area network, right? Local area network is restricted to an organization or a building. Cluster computing also formulated like this. It is set up in a particular area. It is limited to that particular area. It is not expandable, right? And cluster computing also says that if you want to combine the power of multiple computer systems, all the computer systems must have same type of architecture. So we know there is 2 types of architecture, x86 architecture and x64 architecture. So if one computer is x86 architecture, which is participating in a cluster, so other computer systems are also having x86 architecture.
Master and they both have same architecture.
Same architecture. Okay. In fact, the master has no more power than slave. All are equal power, just like a peer-to-peer system. But master is coordinating all the slaves. That is the concept. But it is not scalable, right? Suppose I'll ask you, I need 5,000 system at NIT Warangal. Bring 5,000 system of same configuration. It is practically not possible, right? That's why people have thought that no, we'll not go for cluster computing. Let us find some other solution. So they started distributed computing in the year of 1970. Or later point of time, people have changed the definition of cluster. They call it heterogeneous cluster. Like in a computer lab, we have 50 systems with same architecture. If you go to the next another lab in the same department, you have another 50 systems of different architecture. Okay, lab 1 is having 50 computers with one architecture. Another lab is having another setup, but all the configurations are same. So I will form a first cluster here. I will form another cluster there. I connect. That is called heterogeneous cluster. People have thought that one. So that is actually heterogeneous cluster can also be said to be grid computing. Okay, in another sense you can say. So distributed computing says that it is not restricted to a particular place. One of the true example of distributed system is our internet. In our internet, we have 14 root servers. These 14 root servers are not located in a single place. What if all are placed in a single place? If there is a power failure, gone. Okay. If there is a natural calamity or any cyclone, something happened, the entire network is going to be collapsed. In order to avoid that, what we are doing, we are putting the computer system in different places. Like one of the example, we are using Gmail. Right? Our emails are kept in Google server. But Google is also maintaining these mails in multiple servers. Like Amazon is claiming whatever work you are doing, it is stored in 3 different locations. Same data, you are keeping in 3 different locations. That means it is a redundancy. Right? If you are keeping the data in your pen drive, as well as in your computer system, that is a redundancy. Early days also I used to copy all the things periodically during my PhD time, and I kept in an external hard disk. Okay, because we are using institute computer, something can happen. Okay. What is the problem in that case? Redundancy leads to inconsistency that we have studied in database. If you are keeping data in multiple places, you have to always think that the same data is available in multiple. Otherwise, there is an issue, right? Okay, there is no shared concept like Google documents, right? We are not familiar with the Google documents on those days. What we are doing, we are keeping same thing in multiple places, assuming that everything is synchronized properly. Right? I usually face this particular problem. Nowadays, I am using Google Drive. Google Drive is installed in my mobile. Google Drive is available in my laptop. Google Drive is available in my home computer. So sometimes while I am working at night 9, just I have saved some information, but whenever I am opening at home, the latest version is not updated. Synchronization is important, right? If you make a duplication, make sure that synchronization works. So that is the concept of distributed computing. Internet is an example of distributed computing. Another interesting thing, we have learned 2 architecture. One is called as client-server architecture. Another is called as peer-to-peer architecture. What is the difference? Client-server means server is more powerful. Client is less powerful, right? Server can act like a client also. Server can also act like a client. Suppose a client is making a request to server, and server is having not having that particular resource. Server is making request to another server. So at that time, that server is treated as a client. So client-server architecture is called as request response architecture, right? Client is making a request, server is giving that response. That is a distributed system. That is not a centralized system. Although client server we consider the server is the central point, but that architecture comes under the distributed architecture. Another architecture is called as peer-to-peer architecture. Peer-to-peer architecture, everybody is independent. There is no master-slave relationship. Everybody is equally capable. Okay? In the client-server architecture, if server fails, then client may not get service, right? But peer-to-peer case, computation is hampered. Okay, if 5 people are doing the same work, one person is not feeling well, definitely it is impacting the performance, but the whole system is not collapsed. Okay? So till the birth of distributed computing, there is no concept of personal computer. Whatever we are using today, these are personal computers, right? But there is no concept of personal computer. Means these systems are applicable to a centralized place, some place where people go and do the computation. Like ISA Bangalore is having set up. Many people are dependent on the centralized center. They have to do computation there only. It is not available in every organization. So first non-kit personal computer was developed in the year of 1973. Again, that size is also very huge. After that, first personal computer started in the year of 1974. 1980 is our client server architecture. 1988, ARPANET started internet-based distributed computing. 1990, we have grid computing or edge computing. Edge means our router can be treated as an edge, or gateway is considered an edge. Edge means close to the user. Right? The concept of edge is that you have to always close to the user. Right? Then see, you can notice these two things. 1990 we have edge computing. Nowadays also we are working in edge computing. Right? We are talking about IoT edge cloud. Right? IoT device, edge computing, then cloud. So this concept is not new. Concept exists from 1990. Right? Then cloud is a true utility computing. Utility computing concept is also not new. Utility computing is there in 1990. What is utility computing? Utility means based on your usage. Okay. One of the example I usually give, like electricity bill. If it is a winter season, the amount is less because you are not using electricity. Right? Not much electricity. If it is a summer season, you are using more electricity. So if you use more, you have to pay more. If you are using less, you will pay less. Right? So that is concept of utility computing. Till now, there is no concept of virtualization. Okay, so they started virtualization in 1999. What is virtualization says? Virtualization says that if you have a computer system, okay, that can be used by multiple people. Right? Like our systems are dedicated systems. Either we are using it or we are putting in a switch off mode. But virtualization brings a concept that on top of the physical machine means our computer is a physical machine. We can create multiple virtual machines using this virtualization technology. So one of the popular software we are using, that is called VMware. So through VMware, we are installing another operating system on top of our computer system. Okay, that is called as virtualization. Okay. So for example, in our system, we have a dual boot system. Dual boot means two operating systems. Right? We have Windows system, we have Linux system. The space assigned to the Linux system is different from the space allocated to the Windows system, and vice versa is also true. So both are treated as host operating system. If both are taking different space in the same computer, so we call them as a host operating system. But through virtualization, we have only one host operating system in our computer system, right? On top of the host operating system, I can create a guest operating system. For example, when I switch on my machine, it will load Windows. Then I'll open VMware. On top of the VMware, we'll install Linux. Right? So Linux is treated as your guest operating system. Windows is treated as your host operating system. Between host and this guest operating system, what we have? Virtualization. That is called as VMware. Just like a sandwich. Right? So that is the concept of virtualization. Then the concept of Web 2.0 started. And behind cloud computing, we have Web 2.0. Now we are heading towards Web 3.0. Right? So what I want to convince with this one, all the technologies, whatever we are using today, they are not new. The concept is new. Our application is new. That's all. A new concept started, which uses the old concepts, plus some application is new. Okay, so in 2006, people started the cloud computing. Till the birth of cloud computing, all computings are done for voluntary purpose only. It is not meant for business purpose. Like grid computing case, there are so many projects are there. I'll tell you in the later slide. They never thought of that to will make it a business mode. Like we are also doing innovations, right? But nowadays we are thinking about how to make it a product and sell. That concept is that product development people are doing long back, right? Like if you see BTech first year, we are developing paperweight in our time. right, madam? Right, paperweights and shoe stands. Now people have thought that why not we sell it in a DMart or Reliance and some other things. Concept wise, means business point of view, now we are thinking, right? But people are doing that thing from long back. Okay, so 2006 they started cloud computing as a business model. We will give resource and we will earn money. So they started using cloud computing. Then they started another architecture that is called a service-oriented architecture. The earlier architecture are called as monolithic architecture. Monolithic architecture means, like sir mentioned, there is a large problem, a computer is used to solve that problem. Nobody thought of how this large problem can be divided into small problems. So that started in the year of service-oriented architecture. We decompose the application into small parts or small modules, right, based on the application. And one module we can execute in a particular processor or in a particular computer system. But people are also not happy with service-oriented architecture. They started with another architecture that is called as a microservices. Nowadays we are discussing. Microservices is again decomposing the service-oriented architecture into again small parts. One of the practical example you can say, like we are purchasing from Flipkart and Amazon or any e-commerce site. So you know there is a order receiving unit, order dispatching unit, there is a payment unit, there is a delivery unit. These all are treated as a microservices. So if one of the services is down, it is not going to hamper other services. So we call that as a lightweight services. Here everything is heavyweight. Like when we purchase a computer system early days, the computer shop person, he install all the softwares, right? Basically he install all the softwares without asking you. But whether you need that application or not, we don't know. That's why these machines are called heavyweight machines. Okay, but now with respect to application, we are installing the application. That's why it is lightweight application. Okay, so in 2012, Cisco started the concept of fog computing. Okay. Then people have confused between these two words. One is edge and another is fog. There is a difference between edge and fog, right? If I told you it is near to a particular device, right? Edge means it is near to the device. Which one is near to us? Suppose I have a smartwatch, right? Smartwatch is connected to smartphone through an application. Smartwatch can be considered as an IoT device because it is having sensors, as well as actuators, right? Smartphone is called as our edge device. Suppose we are connecting, yes, our smartphone to a router. Router can be treated as a fog device. Although there is not clear distinction between edge and fog, but a particular application you can take, like I mentioned, smartphone can be considered as a edge device, whereas router, gateway, these can be considered as a fog device. And on top of that, we have cloud. So actually, there is a 4-layer architecture. But in all research papers, either we are using IoT edge cloud or we are using IoT fog cloud. We are not showing IoT edge fog cloud. Very less paper talks about this one. So that is the concept of fog. So people thought that why not fog is replacing cloud? If fog is available to provide the service, why fog is not replacing cloud? Because fog is not going to process massive amount of computation. You think about router and gateway. Router gateway is not that much powerful as a supercomputer. Router gateway is not as powerful as a data center. So fog is providing services on behalf of cloud, okay, to the users, right? So it is near to us. That's why it is going to provide. But if you need heavy computation, then finally you have to reach to the cloud. One of the example, recently I studied a paper related to 5G communication and fog. So they have given a clear case study where they say, suppose I am going to let's say our food street to take coffee. Okay. That person has shown a QR code, right or not? So we are opening our API and we scan to our QR code. Right? Right? What is our objective? Our objective is to pay the money, right? So both owner, means you can say buyer and seller, they are close to each other, right or not? But if internet is not available, this buyer seller both are close to each other, but they will not be able to provide or get the service, right or not? If internet is down, even both of you are close to each other, know each other, nothing to you can be done. You cannot process the transaction. Right? So there is a need of fog. There is no need to go everything there, right? Anything you can do. Like SBI also, the OTP is not OTP case. Then even some offline app, right? They will show some code. You write the code in that app. It will show another code that you enter. Your transaction is successful. No need of any internet. Suppose I am doing any transaction. Now it is asking me for OTP. Instead of asking OTP, it will show a number. And SBI has given a particular app. I will enter the number. It will generate its equivalent number, just like public-private key. I will enter that number. My transaction is successful. So I am not dependent on SBI when I receive my OTP. This is also can be considered as a fog computing, right? Something is given to you, near to you, but it is not replacing bank. By this concept, you cannot replace a bank. Bank is there. If you do any transaction, you will go to bank only. If any dispute is there, you have to go to bank. So even if fog is that much popular, you are not going to replace the cloud. Then 2016, we started a new computing that is called as osmotic computing. Okay, by one of the group of researchers from Australia, they started osmotic computing. What is osmotic computing? It is integrating all the technology into a single umbrella. So, for example, you want to do some computation. Who will decide whether it is solved in IoT layer, or edge layer, or fog layer, or cloud layer? Somebody has to take decision. That is the example of osmotic computing. And if you go for literature, you will find one of the best research review paper, which is published by one of my scholar in Asian transaction on IoT. There is the first research paper, review paper in the field of osmotic computing. So, like that, there are so many other computing paradigms are there, right, that I would like to inform you. Right, irrespective of HPC, right, we need everything, these technologies, in order to process the thing. With respect to application, all these technologies are relying on high performance computing. Now, here you can see there is a hype cycle. Okay, we call that as a Gartner hype cycle. Who is Gartner? He is not a scientist. Like Ohm's law means Ohm's is the inventor of that particular law. Like that, this hype cycle, if you look into, this hype cycle is developed by Gartner. Gartner is a company. That is called a research development arm or company. Right? What they are doing? They are showing this graph with respect to x-axis they are taking time, y-axis they are taking expectations. So Gartner released the cycle twice in a year. Okay, you can see this is the latest cycle, that is July 2023. Okay, this is the latest cycle. Although January 2024 released, but that is not public, available in public source. So what Gartner does, it releases various hype cycles with respect to various technologies. Like AI, ML, it is releasing, quantum computing, it is releasing, cloud computing, it is releasing. So many emerging technologies, they are releasing the hype cycle. So why this hype cycle we need to study? Because this hype cycle shows what is the status of the technologies. What is the status of the technology? Whether the technology is a mature technology or the technology is an immature technology. Suppose I say Nokia 1100. How many people are using 1100? Very less, right? So that is a matured one. Nobody is now interested in Nokia 1100. Everybody is looking in smartphone, right? So that is already absolute. Nobody is now interested how to minimize the cost. Nobody is looking. If anybody is required, then they are purchasing in 1,000, 2,000 rupees. That is economical, right? But everybody wants how you can provide smartphone with less cost. That is an emerging one. So every technology passes through these 5 phases. Okay. Like in human life also we have various phases, marked to there, right? The different phases are there. So every technology case you can find here there is an innovation trigger. Innovation trigger means whenever a new technology comes to market, it is put in the innovation trigger. Right? So gradually that particular technology is used in various applications. So slowly it will move to the peak cycle. Okay. After it will be there in some years a peak cycle. Again, new technology is going to replace the old technology. Okay, like that you can see there is several technology. So my idea is that whatever research work you are doing, you follow this one because industry follows this particular hype cycle. Okay, as academicians we are using, but industry is more focusing on Gartner hype cycle. And you can see there is several colored dots, right? Although these names are not clearly mentioned, but you can see several colored dots, right? You can see there is a yellow color here, or red color cross mark is here, right? What is the meaning of this one? It shows that whether a technology in the sustain in the market for 2 years or 2 to 5 years or more than 10 years, these things you can get. For example, this yellow colored triangle shows a technology will be there in the market for more than 10 years. And you can find a technology here. What is the technology? The technology is quantum computing as a service. So as a service word is not belongs to quantum computing. As a service word belongs to cloud only. Quantum computing is another technology. Merging of quantum computing with cloud is the future and it will be sustained in the market for more than 10 years. So if we can do some kind of research and development in the field of quantum computing as a service, and if you can develop some kind of solution in next 5 years, then it will be a very great thing, right? But don't choose any technology which is less than 2 years. Like you can see in this part, if it is visible, there is a white color dot which shows cloud migration. Cloud migration will sustain in the market for less than 2 years. So there is no need of cloud migration now, right? Already those technologies are developed for cloud migration. They are already in mature state. Already well-defined techniques are there. So you can do research and improve 1%, no problem. But there is no need of such a type of development. But other technologies you can focus, right? Now, another interesting thing is that is called as Google Trend. We normally search a word in Google, right? You try to search a word in Google Trend. So if you search in Google Trend, it will show you the popularity of that particular word. So you can type in your mobile Google Trend and search for a particular word, right? For example, I have opened Google Trend and I have typed cloud computing. Okay. Then once you type cloud computing, there are some other options are there here. Like suppose you want to know what is the popularity of word cloud computing in a particular area, let it be India or in any other country, or you want the popularity of this particular word worldwide, that you can select. So I have selected worldwide. Then the second option says that what is the duration? You want the search query generated last year or last 5 years or 2004 to present. That is the maximum one, right? So I have selected 2004 to present. Okay. So it is showing a graph like this. Right? What it indicates? The peak is arrived. This is a peak, right? Highest one is this one. So always peak is given with the index of 100. And it does not mean that 100 billion search queries are there or 100 million search queries are there. Just we are doing relative one. Out of how many search queries is received by Google, we scale it to 100. Right? So you will see around 2012 or 13, we have received more number of search query for cloud computing. And gradually it is decreasing, now it is increasing. Why it is increasing? Because due to arrival of other technologies which are dependent on cloud, or we need integration with cloud. That's why now you can see the search index is around 50. Okay. Not only this, you can find in Google Trend. If you want to compare one technology with another technology, that also you can do. Suppose I want to compare cloud computing with machine learning. So you will get two graphs. They are search trends. That also you can find. Apart from that, you can also see in which location or which country maximum search query is generated for this particular word. Like here you can see for cloud computing word, the maximum search query is received from Zimbabwe. Its index value is 100. Its highest one is 100, right? And India is in the third position. Okay, that means people have interest in this particular technology. Okay, like that you can get index value of any country, right? By if you put your cursor in a respective country's location, you will get a search index. Not only that, you can also get what are the relevant topics or questions people post in Google. Like when we assign a seminar topic to our student, let's say related to quantum computing, what they will do? They will go to Google, type quantum computing, type column PPT. Quantum computing, type column PDF. Right? So such queries are also coming. Like what is cloud? What is cloud computing? Sometimes cloud computing PPT, cloud computing PDF. These are the popular questions people post in the Google. Similarly, what are the related topics? Cloud computing is related to computing. Cloud computing is related to high performance computing. That also you can get as a related topics. Right? Now, if you talk about India, again, India case also we received the top research, maximum search query during 2012 and 13. Now it is decreasing. Again, it is increasing with the index value of 50. If you restrict to a particular country, you will come to know in which state you are getting maximum search query. So you see which state is coming first. First is Andhra Pradesh with the index value of 100. Right? And Telangana is in 5th position with the index of I think 50 something, right? It is not clearly visible, right? So that you can get from Google. Similarly,
This is true for also persons like scientists also.
this is true for
Persons also. Like scientist names or something like you can.
if scientist name is popular, you will get. Like if you write Narendra Modi, you will get search query. If you don't write your name, you will not get. Okay, if a person is popular, that word you can search in Google. There is no issue. If there is not it will show that there is no search query found. Okay. Similarly, these are the topics and queries with respect to cloud computing in Indian context. Now come to these examples. Why we need actually HPC? So these are the three motivational examples. The first example is that if you consider a cashier or you consider a faculty member who is using a computer system, let's say we are using our computer system for 7 hours per day. Right? We are using 7 hours per day and there are 6 working days. So total how many hours we are using? 42 hours. I am not calculating per day what is the utilization of our system. I simply say that if you are utilizing, I am assuming that it is 100%. On that basis, I will calculate. Right? So 7 into 6, it is 42 hours. Right? But you know, 24 into 7 is the maximum number of hours available in a particular week. That is 168. 24 into 7 is 168. What is our utilization? 42 divided by 168, so 0.25. So 25% of the resource is only utilized. You forget about other hours, right? Only 25% you are using your computer system. How much utilization you are doing, that is different thing in the secondary level. But based on your usage, if you calculate utilization, it is only 25%. So rest 70%, 5% of time, it is completely idle. Now, question arises, as I told you, utility computing, right? Based on your usage, you have to pay. So if I am using 25% in my computer system, why should I pay for 100% of time? Suppose my laptop cost is 1 lakh rupees, right? If I am using 25%, I should pay for 25,000. Why should I pay 1 lakh rupees? That's why this debate is also going in our institute, whether to go for a in-house HPC or we need a cloud-based HPC. Because we are not confident about our own own requirement. Suppose I purchase a HPC system, HPC setup here with a 20 crore and 30 crore. If nobody is using, what is the use? There is no use. But in cloud case, if I purchase a 20 crore resources, after 1 month I can discontinue. And hardly the amount is in some lakhs. That is economical solution. So when the application is applications and view is not clear, then you have to compare with in-house versus outsource. So utilization is only 25%. If you see IBM study or NRDC study, right? This study says that in the entire world, personal computer usage is only 5 to 10%. Personal computer means our laptop, desktop, these are usage is only 5 to 10%. It is true also, right? For example, before COVID or after the last phase of COVID, how much time we are using our system? Very less only, right? or if you take a BTech student or a UG student, they are not using, right? In COVID time only we depended on our system, right? So it is 5 to 10% is the utilization. Server case, it is 30 to 35%. So we have not reached up to 50% also. So although it is done in the old survey, but there are many surveys says that currently also the utilization is low only. We have not achieved 50%. So this question that why we need resources, why we need high-end machines. We cannot achieve a expectable number of expectable, you can say, resource utilization. We cannot reach that particular resource utilization. Why we need a big machines, right? So that is also says that the computing has a major role. You have to think that how to properly utilize your system. Now coming to third example, that is consider a newspaper delivery boy, right? So suppose if you say Hyderabad, population density is very high. Okay, Warangal density is less compared to Hyderabad, right? So if you talk about newspaper delivery boy, the boy is giving you newspaper at your home, right? Suppose out of 30 days, the newspaper is delivered only for 25 days. Are you going to pay for 30 days? No. Right? If newspaper is delivered to you for 25 days, you are going to pay for only 25 days, not for 30 days. Right or not? So the service is not delivered for the rest 5 days. That's why you are not going to pay it. Right? We are not looking at whether there is a cyclone in our city or density of our city or how that boy is coming to, in which route that person is coming. We don't bother about it. We say that whether it is delivered or not delivered. Based on that, we are paying. Similarly, consume. When you travel from one place to another place, okay, nowadays IRCTC also provides meals. So there is an app also consume. When consume, you can enter your PNR number. Okay, through PNR number, they will get all the details, right? Berth number, coach number, train number, and you can select a location. For example, I am traveling from here to, let's say, Vizag. So the intermediate station is Vijayawada, right? So in Vijayawada, I can select a meal, okay, from consume. So it is the responsibility of the consume persons to deliver the meal when my train reaches to Vijayawada. What happened? My train is delayed by 2 hours. They are responsible. That is also true. They may cancel also our order, right? It happened with me also, right? Sometimes it is if the train is delayed for long hours, that they are cancelling, right? But if it is a minor delay, let's say 2 hours, up to 2 hours, they are allowing, right? So they are delivering the train. So whether my train reaches to platform number 1 or platform number 5, I don't care. What I want, the service need to be delivered to me. Otherwise, I am not going to pay. Or even if I have paid, I will ask for refund. So with these examples, you have seen why computing is important. And I want to tell you what is the meaning of a service. If service is delivered to you, you are going to pay for it. If service is not delivered, we are not going to pay for it. Like if you take our Gmail as an example, Google email is an example. We don't know where our Google server is located. We don't know who is managing that Google server. Either Google is managing or Google has given a third party. That person is managing our server. We don't know. Okay. We don't know about location. We don't know about the ownership. We don't know about the maintenance of the server. Storage, other things we don't know. Simply you have given with a username and password. Through username and password, if internet is there, you will be able to see your email. So what user want? If you need a HPC system, I am going to pay. Simply you give me a system. Right? I am going to pay whatever amount per hour or per CPU. I am ready to pay. But I don't want to go for these complexities, asking you that where service is located, which the policies you are using. That techniques I don't want to know as a user. So you need one constraint, that is called an internet. Like if you go for different cloud service provider like Google, Amazon, they are now also providing us HPC facilities. Simply you need to select the HPC facility. You have to agree their terms and conditions. You can use HPC from your system. There is no need to set up your physical machine inside your organization. So there is a chief scientist in ARPANET In 1969, he mentioned a very important thing. He told over 50 years from 1969. So 1969 plus 50 is 2019. He told that before 2019, people will see computing is also an utility. Right? Cloud started in the year of 2006. So although he predicted after 50 years computing becomes the utility, but 2006 onwards, everything is treated as an utility. I can purchase a server from online, right? I can purchase a server from Amazon or Google or any cloud service provider and I can use it. So that is in service. So he mentioned that like electricity is also a utility, telephone is also an utility, LEDs based on the number of calls we are getting bills, right? If number of calls are more, we are getting more bills. If the number is less, we are getting less bills, right? So that is also an utility. So 2019, Professor Kumar, he belongs to University of Melbourne, Australia, who has done a lot of work in the field of cloud, fog, and others areas. He mentioned that computing is a fifth utility. Like as a human being, we have some necessity. One of the necessity is also computing. Like you can see, water is our necessity. Without water, we cannot survive. Without electricity, also we cannot survive nowadays, right? Without gas, also we cannot survive. We cannot cook, right? Without telephone, also we cannot possible. Without computing, is also not possible. If I say stay 2 days with the internet, nobody is willing to do it, right? That's why many Babas are nowadays saying that if you want to do fasting, so you have to keep your mobile phone switched off mode. Okay, it is not the fasting with respect to food, fasting with respect to your fingerprint. Okay, just keep your mobile idle for 40 hours, 48 hours. We'll see what is your presence, right? So that's why it is called as the fifth utility of the computer system. Now, Professor Visira also mentioned about top 500 list. So my request is to go for top500.org site. Okay, top500.org site is visited. People are visiting to know which one is the fastest supercomputer in the world. Okay, fastest supercomputer in the world you will get. So fortunately or unfortunately, US is dominating the first 5. Okay, you can see the first belongs to US, second is also US, third is also US, fourth is Japan, fifth is Finland. And I think CDET Pune, there is a supercomputer they called Hyderabad. Okay, its number is 75. Okay, again, this list is updated twice. Like I mentioned now, Gartner cycle is also updated twice in a year. 20? 27, no, 75. Yesterday I checked. 75. I checked. Okay, it is 75, right? 75th number you will find Hyderabad. Hyderabad is hosted at CDET Pune. LEDs we have a supercomputer called as Param UA2. That was also fastest supercomputer. Maybe another 5 years or 10 years we may be reaching the top 10 list. And this is the list of last November. Right? Twice they are updating this list, just like a competition, right? They found that they are making a competition to know that which country is having the fastest supercomputer. So what is the main observation here? So you think about this core. Just I want to show this one because of this core. The number of cores in the fastest supercomputer in the world is 86,99,904. So let us say it is 86 lakh for easy conversation, right? So think about 86 lakh. That's why this OpenMP, LPA, CUDA programming is more important. Right? If you are writing a sequential programming and you are using 86 lakh, that is of no use, right? If you are not utilizing each and every individual core, there is no need to go for this much big machines, right? And you can see the power consumption for this particular machine is 22,703 kilowatts. I think to run this supercomputer, we need this much of power, right? And you can achieve 1194 petaflops per second. So you calculate million instructions per second, right? So like teraflops per second or petaflops per second, this much power you can expect from this particular supercomputer. Okay, so this is the definition of computing. I am not going to tell. SEM mentioned computing is a goal-oriented activity. Anything you want to do, If you want to achieve a particular goal, that can be considered as a computing. And in this, we call that as a calculation. Right? I am adding two numbers. We call that as a calculation. But we know if we go beyond a particular limit, it is not possible for us to do the calculation. Like if I ask you to multiply two 10-digit numbers, it is difficult. But if with a well-formed programming language, you can do it. Right? So that also we are doing some kind of computation, like a help of our computer system. So that is also a goal-oriented activity. So computing is considered as a goal-oriented activity. Now, I'll focus on, like I mentioned, so many computing technologies, but I'll focus only on these computing technology. We'll start with the distributed computing or parallel computing, or sometimes we call it parallel and distributed computing. Whatever computing paradigm you know, these all are coming under parallel distributed computing. Cluster, grid, cloud, fog, osmotic, whatever computing, quantum computing, all are family of parallel distributed computing. After that, we will discuss cluster, then we will discuss grid, then utility, then cloud computation. Okay. Now see this example. Here we are showing the difference between the centralized computing and distributed computing. This is an example of a centralized computing. We have a mainframe computer and clients are connecting to the mainframe computer. So this client is requesting mainframe computer to provide some resource, and mainframe computer is providing that resource to that particular customer. Okay. So the problem with this one, if mainframe computer is failed, or we call that as a single point of failure, SPOF. If there is a single point of failure, these terminals cannot get the service. That is called a centralized computing. When you go for distributed computing, everyone is independent, right? I told you, like here you can see these are three different workstations. They are connected through a network link. So if a computer system is failed, performance will definitely hamper. You cannot say that performance I can achieve, but overall the system is going to be collapsed. Right? For example, suppose you want to do 1 plus 2 plus 3 up to 100. You want to add these numbers, right? What you will do in distributed system? First person you will say you calculate 1 plus 33. Second workstation you tell calculate from 34 to 66. Next computer you ask to calculate 67 to 100. So they will do parallel calculations. After that, what you will do? You will consolidate them by adding these three sums. So assume that a particular system is failed. This system is failed, which is calculating 1 plus 2 plus up to 33. Performance will definitely hamper. Right? Now this 1 plus 33 need to be either computed by this machine, or they will divide again it into two parts. Let's say 1 plus or 2 plus up to 16 and 17 plus 18 plus up to 33, and they will compute it. Performance is hampered. System is not collapsed. But in this case, performance is also hampered. System is also collapsed. So earlier systems are standalone systems, right? All the layers, whatever we are seeing, presentation layer, logical layer, control layer, data layer, everything is done in a single system. That's why the system is bulk. It is a very heavy system, right? Heavyweight system. But nowadays we have lightweight system. Like if you consider this is client and this is server, we have studied some term called as thin client and thick client. Thin, 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 thick client. Similarly, there is a thin server, thick server. Right? What is the difference? Thin client means it is taking only less responsibility. Okay. Thick client means it is taking more responsibility. So always there is a pair with the thin client with thick server, or thick client with the thin server. One side you have to take thin, another side you have to take thick. In that way we are connected. Right? So these are layers, whatever we have, I told you, presentation, control, data, these are shared between client and server based on whether they are thin or thick. Thin means you will take responsibility of very less layer. Thick means you will take responsibility of more layers. Okay. So early computings are done with a single processor system. Okay. They never thought of multi-processor system, single processor system. Like we studied in operating system, there is a concept of multi-programming. Okay. Studied or not? Multi-programming. Is it possible that two programs run at the simultaneously? Then why we call that as a multi-programming? You know, process state cycle, right? So we have also shown you a diagram. We have seen something is new, ready, then running, IO, then again waiting, something like that. Is it possible in the processing part, you have more than one processor at the same time? Process. More than one process at the same time? No. Then why it is called a multi-program? What is the reason of saying multi-program? Multi-program means multiple program, right? General sense says. Why you are saying it is multi? It is single programming only.
Programs are loaded and the cycle is waiting for some reality. Then start program will immediately.
Okay. If a system, if a particular process require IO, it will go to IO. At that time, another process you are loading into the running state, right? So together you have multiple programs. Whatever we pointed in the ready state also we have, waiting state also multiple processes. The running state only one. So whole looking into the entire architecture, we say it is a multi-program. Or you studied about pipeline, right? You know, first you have to read a instruction, right? Fetch, we said is fetch, right? Then read something, suppose something from memory. Then you can write something into the memory. Some phases are there. So if an instruction is entering to another phase, other instructions are in waiting. After fetch, let's say read. So one will move to read, means another will load in the fetch. So at that time, multiple processes are there in the line. That's why we call it that is pipeline. But here it is single system. Early systems are only single processor system. And universal computing can be also a centralized computing. So like if you call about supercomputer is located in a particular place only. Like we have access up to IIT BHU supercomputer. Okay, in this project, NSM project, which is sanctioned by IIT Bangalore of 50 lakhs, they have given 14 lakhs to IIT BHU so that we can use their server. Okay, that is in IIT BHU server. That is a centralized computing only. Although you are doing parallel processing should not be confused with centralized computing. Okay, if IIT BHU is having power issue, it is gone. Like in the whole about the country, there are many places where supercomputer is there. IIT Hyderabad is also having a supercomputer. Right? So they have given remote access to that particular computer system. We want to achieve parallelism, but facility is centralized. So supercomputer is considered as a parallel computing. We are not calling it a distributed computer. Distributed means it is not located in the same place. That's all. Supercomputer is placed in a single place. That's why it is a centralized computer. But in whole India, there are 75 supercomputers are there. Right? If I combine them and do some kind of computation, that can be considered a distributed computing. So they are not located in a single location. Okay, so distributed computing and distributed system, that is important. Also, in computer science, we have a subject called parallel distributed computing. Sometimes some institute is writing parallel distributed system. There is a difference between system and computing. System means we are talking about computer system. Computing means what we are doing inside it. Right? So distributed computing is a field of computing that studies distributed system. Okay. We study the distributed system in order to achieve the computation power. So if you consider this one, this particular diagram, I have taken 4 different processors. Right? I have taken 4 different processors. Each processor is having memory. Right? And that is personalized memory, or we call it a local memory. So whatever local memory this processor has, it should not be given to another processor. Okay, but when this is a distributed computing, if I say that all processors are located in different places, it is a distributed computing. But if you talk about parallel computing, we have a shared memory. Okay, we have a shared memory. So if you want to do something, you have to go to request that memory, retrieve it, and do it. Like in database, we have studied X value is 5 used by one particular person. That person has modified 5 to 10. Another person is making a request. So he will get the updated copy or not. It's an example of shared memory. But the distributed memory, they don't care, right? Its memory, whatever happened to this memory, others are not caring whether that memory is there or not. Nobody cares, right? So shared memory concept is there in parallel computing. Distributed computing case, we have local memory. That's why parallel computing is called as a tightly coupled system. Something is tightly coupled. So if anything happened to one, it is impacting other. But distributed computing is said to be loosely coupled system. Loosely coupled system. Loosely coupled means if one happen, anything happened to one, that is not going to impact another system. It will impact, but not in that way which we have seen in the parallel. Okay, that is the basic difference between parallel and distributed computing. So many people have look this distributed computing in a different perspective. Like with operating system perspective, we say distributed system, or you can say some other definitions are also given by various websites. These are some of the examples of distributed computing. Internet is a true distributed system, I told you. ATM machine is also a distributed system. The main problem with distributed system is synchronization. Right? I told you Google Drive example, right? If I download a desktop Google Drive in multiple systems, if something happens, then it is impacting all. Right? So distributed computing and synchronization is the major issue, which is not there in the parallel computer. Like in a particular computer system, you have 8 cores. Okay, communication mismatch will not happen. Right? But these 8 processors, suppose I talk about 8 processors located in 8 different locations, then mismatch may happen. Like if I ask you what is the time now, everybody will tell different time. Right or no? Although we have following the Indian standard time, but you see your wall clock or you see your mobile phone, you will get a different time. That is a synchronization issue. Right? Suppose I have coordinated a message to you. Right? Let's say 1 p.m. I have sent a message to you. You have received it 1-1. Okay. Just before receiving the message, you have sent that I have not received the message. Before 1 second. So I got an acknowledgement that 1-1 you have received the message. Right? But you have sent me a message, I have not received it. Now my perception is that you have not received the message. And again resend the message. This happens with respect to synchronization issue. Synchronization is the major headache in the case of distributed system. There is a book that is called fault tolerant computing. We says about there are a lot of methods. You can see with example. We say that how to synchronize every machine. There is a concept called a checkpointing. Checkpointing can solve the problem. Okay. Checkpointing can solve a particular problem. This is a different story, so I'll tell later on. Okay. Intranet work group is also called as a distributed system or distributed computing paradigms, you can say. So what are the components of a distributed system? Anything can be considered as a distributed system. In my mobile phone also I can do some kind of computation. So mobile phone is also a component of the distributed system. PCs, workstations, symmetric multiprocessors, whatever you have, these all are called as a distributed computing system. So there is a platform you can search that is called as BOINC, which we call as Berkeley Open Infrastructure for Network Computing. Try to install BOINC in your system. Later point of time you can uninstall it. Right? So this BOINC platform, was developed by University of Berkeley, US. So what they did, all the voluntary projects like weather forecasting, there is a project. Finding the drug for malaria, there is a project. We are playing some game, that is also a project, right? Like that, around 50 projects are hosted in this BOINC platform. Okay, BOINC is a platform. Inside that, we have so many projects. And this platform do not own a single machine. This platform is not owning a single machine. But anybody who wants to contribute to BOINC platform, you can simply install BOINC, add a project to that in that particular platform, and your system's clock cycle can be used by the BOINC platform people. Okay. So you will see once you install BOINC in your computer system, adding a particular project, you will see the utilization of your system will reach more than 90%. We are talking about 25 utilization in the example. But once you install it, you will receive up to more than 90%. You will get almost 99%. Why? Because whatever project work they are assigning to your computer system, there are a lot of parallelisms are there. Like a sequential program, your system will not utilize. If you do a parallel program, definitely it will utilize. So try to install VONs in your platform. There is no need of any security issues. Don't think about security issues because these are voluntary projects and these are the real life projects. Like weather forecasting. What is the temperature of tomorrow in a particular place? It is done with weather forecasting project only. So it is running under VONC platform. Right? That is also an example of a distributed system. There is a project, famous project that is called as SCTI at home. SCTI stands for Source for Extraterrestrial Intelligence. Okay, it is the astronomy related project at home. In this project, every time it is observed that more than 5 lakh machines are active, and none of the machine is owned by University of Berkeley people. People have contributed the cycle in such a manner that at any point of time, anybody can join the system, anybody can leave the system. Suppose I install my VONC in my system and I will leave my system. Or I switch off my system. So I am exited from that particular platform. But peak we have seen that in average, we have 5 lakhs number of users are contributing to this particular platform. That is an example of a distributed system. Some of the common properties of distributed system is that first one is called as fault tolerance. Fault tolerance is that even if there is the existence of fault, your system should work. Like if you consider airline system, in airline system we have 2 engines, right or not? Even if one engine is failed, aircraft is not going to be crashed, right or not? Even if it is a fail, another machine is that much capable, you can reach to the nearest airport, right? So normally in fault tolerance system, we have a formula called 2n plus 1, where n is number of fault. In a particular system, if you consider the number of fault is n, then you need at least 2n plus 1 number of system. So if I expect that in my system, whatever system I have designed, number of fault is 1. So 2 into 1 plus 1. So at least 3 systems should be active at the same time. Right? To achieve the fault tolerance. So why if one or more node fails, then the whole system can still work fine. Okay, the system can work, there is no issue. Right? But performance is hampered. Right? Performance will definitely hampered. That's why it says that it will work fine, but performance may be degraded if a system is failed. And none of the node plays a full role. In distributed system, there is no master-slave relationship, right? Everybody is independent. So every node is not playing the full role. Full role means it is powerful. Everybody is contributing little bit to make the system. That's why it is mentioned that each node play a partial role in distributed system. Next one is resource sharing. Why they are contributing? Because to share resources. Sometimes you need resources, I will provide it. Sometimes another person requires, he will take from us. Right? Like if you take an example, assume that there are 3 different organizations, A, B, C. Okay, these 3 different organizations, A, B, C, and they are having 10, 20, 30 number of servers. 10, 20, 30 number of servers. Okay, suppose you need 35 number of servers to execute a particular application. They have 10, 20, 30, right? We need 35 servers to run an application. So individually, these organizations are not fulfilling the requirement. Because first requirement is 10, not possible, 20, not possible, 30, not possible. What they will do? 10 servers organization will collaborate with 30 servers organization. So together they are 40. So they will create a virtual network by combining these 2 organizations to run a particular application. Or 30 will add with the 20. Okay. And together they are 50. So 45 server 35 is my requirement. They can do. Okay. That is called as the process of resource sharing. Next, come to load sharing. Load sharing is another important part. I also mentioned related to load sharing. You know, we have studied one algorithm called as round robin algorithm. Right? Round robin is equally distributing the load among everyone. That is written, right? But it is not true. Right? Suppose there are 100 food packets are there and there are 50 persons. Right? Round robin says that everybody will get how many packets? 2 packets. But round robin is not looking who is hungry, who is full of stomach. Round robin is not looking at. Round robin is doing with respect to the number. In that way, it is fair algorithm. But if you look into the load, that it is not looking. It is simply distributing. When you assign the two works to a computer system, what is the guarantee that the system is not busy? The system may be overloaded. Again, you are giving two tasks. Another, what about two tasks you are giving to a machine? It may take 2 hours. Another machine you are giving two tasks, it is taking 2 minutes. So distributing with respect to number is not the solution. You have to understand the load of each and every machine. Then only you have to assign the task. So that is coming under the load side. And easily you can expand, right? Today you are happy with 100 system. Tomorrow you want to add another 100 system. You can add in distributed system. Like I told you, VOINC. At any point of time, the number of machines may be increased or may decrease. In average, it is 5 lakhs, right? And performance-wise, if you see, parallel computing is a subset of distributed computing. So distributed computing case also we are getting parallelism. I'm not saying for distributed computing we are not doing parallelism. Parallel computing you are doing in a single place. Distributed computing you are doing that in multiple places. Why we need distributed computing? First you look into your application. Like if an application is not decomposable, that is not possible to apply distributed computing. You cannot divide a work. Whatever work is there, let's say only one person can do. There is no question of distributed computing, right? That is not possible to distribute that work into multiple people. And if you look into, if you decided that no, we can decompose it, then you have to decide whether your task is computational intensive or your task is data intensive. What is computational intensive? You need lot of computation. Like if I want to calculate the value of pi. Let's say I am using Monte Carlo simulation. In Monte Carlo simulation, you have to take set of input parameters. Suppose 5 parameters are there. You have to specify their range. Range means minimum value to maximum value. You will generate a data set and you will compute it. So, for computing the value of pi or computing any mathematical simulations or something like that, you need computation. Data is important, but computation is more important. That's why we call that as a computing intensive application. But if you look into Facebook, okay, Facebook, you look or any social media platform, Twitter, what we need? We need more emphasis on data rather than computation. It doesn't mean that the computation means data is not there or data is means no computation is there. That is there. Which one is more important? So Facebook or you can see if you go to grid computing, there is a called as Large Hadron Collider, LHC we say. That is example of our data intensive application. And obviously distributed computing we are using to avoid no single point of failure. Right? You will not get any kind of failure. Even if there is a failure, other node can execute the same task without any issue. Right? Now, we'll take another 2 slides, then we'll start. Now, if you go for distributed applications, there are many scientific engineering applications are there which are distributed in nature, right? So this we have seen, like these are the clients, they invoke to the server. This client has made a request which is called as invocation. If server is having the resource, server will return the result. If server is not having the resource, the server will treat itself as a client and making a request to another server. So this invocation and result is the request response. That's why we call it request response mode. But in this case, what happened? A set of servers, right? A set of servers are providing services. One may provide computation, another may provide data, another may provide network. So any client is making a request to a particular server, okay? And the server, if the resource is available, it will provide. Otherwise, they will communicate each other and finally provide the services to the client. So we consider multiple servers as a single unit. That's why it is called a service provided by multiple servers at the same time. User is not aware that who is actually providing the services. Okay. Okay, then peer-to-peer computing. Like in the case of client server computing, we have some master slave relationship, but that type of computation is not there in the peer-to-peer computing. Like here, this is an example of peer-to-peer computing. You can see these are peers. We have multiple peers, right? And each peer is having multiple objects, right? Suppose you can see this particular peer, we have 5 different objects, right? 3 objects may be used for locally, right? Or 2 objects are used in locally, and these 3 objects are sellable. Sellable means they can sell to peer 2 or peer 3, peer 4 based on the requirement. They are not selling the whole resources because you have to do local computation also. You have to handle local computation as well as you have to participate with others. Okay, that's why together they achieve a particular application or solving a particular computational problem or any applications. That's why peer-to-peer computing is more famous in comparison to any other computing. Okay, we'll stop here. In the afternoon.